Hello, everyone, and welcome. People will be joining over the next couple of moments, I'm sure, but welcome to our virtual Whitman Computer Science Capstone Conference. As many of you know, the intent originally was for our senior class to be able to present their capstone projects as a part of the Whitman Undergraduate Conference. That conference was canceled due to the COVID-19 pandemic, for which we were very sad to lose that opportunity. But now we have the opportunity to invite an even broader audience to see what our seniors have done. And so I would like to point out this is the schedule that we will be nominally following. We've got 5 presentations. The goal will be to kind of keep on a half-hour cadence. We'll start the presentations no earlier than the times listed here. So if you needed to drop off and come back for a specific presentation that you were especially interested in, feel free to do that. And otherwise, feel free to ask any questions. We will be using the Q&A feature of the webinar to moderate questions. So if you do have questions, feel free to enter them there. And then kind of towards the ends of the presentations, I'll be moderating those and passing them along to our panelists. So with that, I would like to introduce our first presenters presenting Building an Automated Crossword Solver. We have Maddie Crowley, Raylong Zhuang, Yuan Jiang, and Andrew Yeon. So I will stop sharing my screen and invite all of those panelists to join. Welcome, everyone.
Hey.
So who will be presenting? All right.
My screen should have just shared.
Yep.
Awesome.
Excellent. All right, go ahead and take it away.
All right, let's get started. So our capstone group is called the Double Crossers. My name is Maddie.
I'm Raylong.
I'm Yeon.
And I'm Andrew.
All right. So first of all, we're going to talk a little bit about the problem that we were tasked with solving. So we were asked to create a computer program that, given the input of a set of clues and the corresponding crossword grid, would output a correct set of solutions to the grid. So here, first, we just have a little example. This is a New York Times mini puzzle. So this is kind of the format that we were looking at throughout most of the solving of our project. Yeah. So we wanted to talk a little bit about some conventions of the American crossword puzzle, just in case people aren't fully aware of what that consists of. So first of all, it's a numbered grid that's intended to hold words that overlap horizontally and vertically. And there are clues for each word down and across labeled by the number that matches the grid. Each white square will contain a letter that you'll input, and the black squares are intended to block space, maybe at the start or end of a word. The words are generally 3 or more letters in length, and this part of the speech of the clue and answer are intended to agree. So we wanted to talk a little bit about how a human would approach a crossword. So first of all, you start with background knowledge. You use your previous knowledge and experiences to try and solve each clue. Understanding language. So all the clues take many different forms. It can be a fill in the blank. It could be a person that you're looking for. So a lot of the times you have to try and understand what exactly the clue wants from you. And then third, guess and check. So a lot of times we'll make mistakes when solving crosswords and correct them later. And so if you fill in a spot with an incorrect word, eventually that mistake will prevent you from filling in other words. So you have to backtrack, which we'll talk about a little later, and try and figure out where you went wrong. And so we take into account all these same factors when we're teaching a computer to solve a puzzle. So as far as our strategies go for solving this problem, we were looking at 3 different things. An algorithm for filling in words first. So we have to traverse the crossword puzzle, which means temporarily putting words into spots in the grid and backtracking if we find out that they're wrong. Examining clues. So again, clues take many formats and we have to understand the clues and what they're looking for. And then we also have a database of clues and their respective answers. So we need to know, like if the clue we're looking for and the clue that's in the database are an exact match, how do we tell how similar clues are and decide which to try as an answer in our algorithm? And so we're going to talk a little bit more right now about how we implement all of these strategies.
So for the database, we use the database created by Professor Matthew Ginsberg, and it contains 3.8 million clues, and it's all collected from the past crossword puzzle that's published by New York Times and some other publishers. And the database is divided depending on the length of the answer from 3 to 15 letters, and they're stored into corresponding text files.
So yes, as Maddie mentioned before, like human being doing the crosswords, the guess and check part was we modeled the guess and check part to be a constraint satisfaction problem. So in mathematics, a constraint satisfaction problem is characterized by 3 parts. That's the set of variable from x1 to xn, and also for each of the variable, there's a domain that have the possible values for that variable. And also coming with the problem, there's a set of constraints, and usually the constraint would be the relations, and this constraint has to be hold true between the values of the variables. So how does this apply to our crossword puzzles? We will see that if we can go to the next slide, please. So yeah, when we're looking at the crossword puzzle as a constraint satisfaction problem, then for each of the variable, that would be the line that we're going to place the words into it. So as the example shown on the right, we have like the vertical and horizontal grids that we need to fill in the words, and each of the line will going to be a variables. And then for the domain for our problem would be for each of the variable would be the English word that we're going to fill in. So for example, for H1, we are right now filling words by shop, and then we also see for V6, like the vertical V6 columns, then that for the domain for that variable, we're going to be all 5 letters English words. So then the next thing would be the constraint. Then the constraint in our problem would be the letters that where 2 variables intersects. So as the example for H1 and V2, if we're filling the words by shop for H1, then the constraint that we impose for V2 would be that the V2 has to be a words that starting with the letter I, and therefore in our case we're filling a words Intel into it. Besides such kind of constraint, the hints and it can also be viewed as a constraint in our case, because the hints from the crossword puzzle actually tell us what kind of domain that we have for each of the variables. That's the next things that we want to talk about is how do we approach in solving such kind of problems. So the first thing I want to talk about is the backtracking search that we have. So backtracking search is actually a pretty typical approach in solving such kind of problem, and it's being defined as a depth-first search that chose the value for one variable at a time and backtracks when a variable has no legal value left to assign. So this might sound very confusing, but then I'm going to use a very classic and simple examples that's in constraint satisfaction to illustrate this idea. So the problem would be the map coloring problem. So for this problem, we are trying to assign color to each of the region in this map, and no two region that next to each other will have the same color. And then if we want to assign color to each of the region, then we need to have a starting point. So if we start from an empty maps, then we want to start assigning the color to the very left regions. That would be the very left regions. Then the color that we can assign to it would be red, green, and blue. But then we would look, by performing that first search, we will first look into the red colors to see how if we assigning the red color, and then we know that the second ones would be only valid if we to assign for green and blue. And because we are assigning value in order, we have red, green, and blue, but then red is an invalid color to be assigned, so therefore we backtrack to the second layer and then reassigning green. Therefore, green is a valid one, so we keep doing the assigning value to the next layer. That would be yes, and then we will keep assigning red, green, and blue, and we will therefore seeing if we're going to perform that first search on the color green, assigning to the search variable, then we're therefore causing a backtrack to looking for the next variable that we want to assign in the value. So therefore, by performing such kind of things, we can know that our solution is definitely going to satisfy all the constraints and become a valid solutions. And particularly for our problem, we are implementing more techniques to help us. The next things that we want to talk about is the constraints propagation. So constraint propagations refers to the technique of looking ahead in the search as the yet unsigned variable. What does that mean? That means we are trying to detect if there's any obvious failure that have occurred in our search. The obvious here means the things that we can detect or test efficiently. In this search, even though we don't have detect any obvious failure, that we might be able, then we still might be able to eliminate some possible part of the future search. So in our case, that would be the words that we're filling into the grids causing the variable have empty domain in the future. So if we're filling any words that causing the other part of the search trees have empty domain, then the words that we're filling in would be invalid. Therefore, propagation is actually very important in constraints propagation. Actually, very important in solving our constraint satisfaction problem. And this is going to be applied at every node of the search tree. So there's some trade-off doing this, because when we're searching fewer nodes in our search, then we will have higher nodes processing rates. But if we want to looking ahead more nodes, then that will slow down our search in our search tree. Therefore, we need to be careful using this constraint propagation. And the next things that we use, the technique that we use in solving constraint satisfaction problem was the cheapest first heuristics. So we want to assigning the value from the most constrained variables, which means the ones that we are most confident about. Therefore, by avoiding making mistake at the early stage, we can hope to have shortened time in trying out the ones that is not going to work out for our problem. Therefore, by using such kind of techniques, we can be better guess and check the solution we can fit into the puzzles. So after talking about the guess and check part, the next part we want to talk about is how do we figure out the domains, like the legal value that we are able to fit into the variable or into the grids. That would be the natural language processing. Sorry, Maddie, you need to unmute yourself.
Thank you. All right. So natural language processing is basically an area of computer science that tries to help computers understand human languages. And in our case, that is English. So if you imagine if every word were simply a set of characters that you didn't know, then how would you start this process of understanding their meaning as far as grammar and word meaning or multiple word meanings go, etc. So NLP uses concepts in machine learning, which is a subset of artificial intelligence that helps the computer learn from experience to interpret meaning in language. So you can see on this, in this figure on the left, how computer science and linguistics kind of overlap along with machine learning to help us do that. And we'll talk a little bit more about how we use this to understand if two texts overlap and how much they overlap. And we use that to score. Let's see here.
So one very important part in our in understanding the hints and figuring out what words is being related to the hints that in our task is to extract the sentence characteristics. And the most common methods of estimating the baseline semantic similarity between a pair of sentences, that's one from our database and the other one from the is the hint from the crossword puzzle. We are trying to averaging the word embedding of all words in these two sentences and calculating their cosine similarity between the resulting embedding. So for example, if we have the sentence such as how old are you, what is your age, my phone is good, then we do some word embedding and vectorize each of the sentence, and then we input to our algorithms and to figure out how close, like how similar they are. So here we can see there's a similarity matrix showing here. So we can see how old are you are definitely identical to how old are you. So therefore it's very closely related. And also we will see what's your age is very closely related to how old are you. By using such kind of techniques, we can figure out, we can compare the meanings, how similar the meanings of the two sentences.
So this is the formula that cosine similarity uses, and it is a measure of similarity between two non-zero vectors of an inner product space that measures the cosine of the angle between them. And for the angle that is 0 degree, the cosine for it is 1, and any angle that is between 0 and pi, it will be less than 1, and we only compare the orientation of the vector. And if two vectors with the same orientation, it will have like a cosine similarity of 1. And if two vectors that are opposed, then we will have a cosine similarity of -1. And the advantage of cosine similarity is it will not affected by the Euclidean distance. So it means that it won't affected by the length of the two clues.
So in terms of the cosine similarity, we are actually comparing the words in the sentence to see how does the words is similar in two sentences. Therefore, the baseline for that would be the baseline for such kinds of approach could be improved by the methods such as ignoring the stop words, and also calculating the and also by computing the average weighted by using a lot of methods. But the next thing is we want to extract the meanings of the words by using a technique called word mover distance. So in word mover distance, we can actually seeing how close two words is being related to each other in a vector space. So for example, in our the example that I have is based on word-to-vec embedding. So in word-to-vec embedding, we can vectorize each of the words, and by having such kind of a model, we'll know how close they are to each other in the vector space. For example, the Obama is more close to presidents compared to the other words such as speaks and greets, and also speaks is close to greets relative to the rest of the words. By having such kind of things, we can add another layer on our cosine similarity to have better representing the similarities of the meanings of the sentence in our programs.
So yeah, Rilong mentioned word embeddings earlier from Word2Vec, and I just wanted to clarify what Word2Vec is. So Word2Vec is a method of word embedding that uses a two-layer neural network to train on a corpus to create a vector space that accounts for the linguistic context of words. So let's just unpack that real quick. What this basically means is neural network is a machine learning algorithm that is designed to recognize patterns. And in our case, the kind of patterns we want to recognize is the linguistic context. A corpus that we're going to train on is just going to be any old block of text. In our case, it was all the clues in our database, but it can be just something as simple as text messages or chat messages. And to our right is exactly the kind of training that we're going to want to see. So for example, let's take 3 words from some corpus, king, man, and woman. This is what's going to be called an input layer. And this is what we're going to pass into Word2Vec. And Word2Vec in like the middle area where you see these 3 dots is the hidden layer, and that's where all the training happens. And in that, you see a bit of what you see with the cosine similarity, where we see the mover's distance interacting with each other. And out to the right, the last thing, you see a bunch of colors. That represents the embedding that you would typically see with these words. And with those, you can see a perfect example of the kind of differences you would see amongst the distance is like looking at man and woman. The first 3 colors for them are very similar, except the last one. And that is the kind of differences we want to see in terms of linguistic context for one to another. And so this is actually a very infamous example of Word2Vec in use. So in the next slide, we're going to see example of a code version of it. Right here, we call model.mostSimilar, and positive equals king, woman, negative equals man. So just to quickly clarify what each thing means, positive, the 2 words that we're going to pass into positive are what's going to give our probability a higher score, and negative is what's going to take away some of the embeddings that we mentioned earlier and recalculate it based on that. So if you think about it for a second, king, woman, negative man, the highest results that Word2Vec should give us is queen, which is, of course, in this model, what is represented here. So in our case, though we didn't quite use Word2Vec, we did similar techniques with mover's distance. Here are 3 examples of the domain output that we would see if we ran our code. So for example, here is a hint, lines on a music score. We would have some array, and in this array, we would have a descending order of scores based on each of the domain possible words that we can have on it. So as you can see here, after applying our scoring function, we can see staff is our highest in terms of score, as opposed to lento and seto, which are a little lower than that. And yeah, these other 2 clues, we can see an example of fill in the blank on the second one, are just the kinds of things we would typically run on our code and see in our domain.
So in terms of also like in our program, there's a lot of problems that we think there should be more improvement that we can do in the future. For example, in the constraint satisfaction problem, we found that when we were running a program on different kind of puzzles, we were seeing that some of the constraints matters more than the other ones. So we were thinking a weighted constraint satisfaction problem would be better in terms of improving the performance of the guess and check part. what does that mean? It means that we can assign different values to different kinds of constraints in our problems, so that we can better to figure out the score of like the orders of the variables that we're going to assign the values on. And the next thing is that when we are running our program on larger crossword puzzle, which is like around 15 by 15, we are actually suffering a lot on a problem that's making from the problem that's making early mistake. What does that mean? It means that if we assign a value to a variables that's not going to work out for our problem for the crossword puzzle, it turns out we will waste a lot of time in searching through the search tree. That's not going to be coming out a solution for our problem. Therefore, we think a limited discrepancy search would be a way to solving this kind of problems. So by adding discrepancy in our search, we will be knowing that at what points we need to go back, and then we know there's some points that we don't need to necessarily searching through the whole search tree, by only looking at the partial solutions to the problems. Next, we want to talk more about the problem from the NLP part.
Yeah, so we talked about word embeddings and comparing the similarity of sentences earlier, but we also worked on other parts of natural language processing, mainly part of speech tagging and parse trees, which basically allows you to get the part of speech of each word in a sentence and also break it into chunks, whether that be phrases or compound words, so that you can also get the part of speech of each of those chunks. And we looked earlier in our presentation, we talked about clue and answer agreement. So this is one of the rules for American crossword puzzles. And we can basically use that rule to compare the clue that we're looking for an answer to and our database in order to find out if they agree. And so we worked on this, but ended up not implementing it because of inconsistencies in our output. And also we had a lot of different types of clues, one of which we've talked about is fill in the blank. So specifically for this, the part of speech agreement doesn't work because you're looking for the part of speech that would be included in that sentence.
Right, and the last future work or improvement that we have considered is those involving Word2Vec. So earlier we mentioned about the kind of techniques that Word2Vec uses. We didn't necessarily use the Word2Vec that comes with the program that we ran our code in. And the reason we didn't use the built-in Word2Vec and instead use Word2Vec-like techniques is because we have done training on this before, but we've decided because of time constraints, we would not be able to finish implementing it fully. So we made a model. We used 21 online encyclopedias instead to train on. These were free and you could just access these easily. And the results that it came up were actually very promising. But the issue was that, well, there were a few issues. The first issue that came to mind was when it came to pop culture, contemporary, like people incumbent in government offices, all these things, this model was not efficient in solving. So you might say, for example, maybe we should use a bigger model or use more things to train on. But we found very quickly that training takes a very long time. And you would have to tweak a lot of parameters and settings, like how much workers or like the min count for that. And we also thought that because it also takes a long time to train and it takes up a lot of data, we would also probably need a dedicated server or even dedicated hardware to go through with this. But in the future, if we do decide to implement Word2Vec further, we can see like what kind of communication can we do with our existing cosine similarity function. Can we use it together, maybe find the average of the two, or we can improve it just on its own and maybe use it as an alternative instead.
Yeah, so that's the end of our presentation. Thank you so much for listening, and let us know if you have any questions.
So we had a couple of questions from the attendees. So one was, when humans are solving crossword puzzles, if they discover a mistake, then what happens is you go back to specifically the answer that is causing a conflict and fix that one, which basically does the backtracking out of order from the order that you had filled in the answers. Does your algorithm do anything like that?
So actually, our program does not cannot do the backtracking out of order because of the design of the depth first search, but we are trying to exploit the capability of the machine as much as possible. So we will know that kind of we will have the confidence on the words that we're going to assign into the variable at very first by going through all of the hints. At that point, the machine would have a overall kind of sense on the confidence on which hints he's best at, and then by keeping that order, filling the most confident words in that order, and therefore have a very good starts on eliminating the backtracking, because backtracking actually very expensive in our program in terms of like the times that spent on solving the puzzles.
Mm-hmm.
That answers the questions.
Yeah. So another question was, how do you determine whether your crossword puzzle solver is good or not? And like, how do you measure the effectiveness of a crossword puzzle solver like that? And do you have any information you can share about how you've measured your solver?
Andrew, do you want to answer this question?
Sure. I was actually going to answer the last one, but I could probably also answer this one.
Okay.
So let's see. How do we assess the performance of our crossword solver? I would say what we typically do is we like to store the results of the domain and a probability. And what we do is after the code is run through, it gives us our best result, and we save it in some, I guess, text file or some dump file. And then what we do is so the first thing we need to clarify is that the test, we have a training which we go through, which is the clues itself, and we run all of this stuff on our training. And the test, which is the only thing we extract from a test are the clues. It was only after we have our best results that we refer back to this test and check the actual variables and what were placed into each, and then we compare from there. We don't have code telling us exactly like, oh, the % right or the % wrong. What we just have is our results, and then we pull up the test results, and then we just look at it manually. That's kind of how we assess the performance of our crossword solver. And as to whether or not we know how our algorithm performs on such metrics, I would have to say how well we know our algorithm works is mostly contingent on the kinds of clues that we run into. So I guess that also feeds into the final question. So all things considered, our algorithm is limited in that we tend to work better and faster on smaller puzzles, and if the clues are consistent and follow a pattern that we can recognize. And that's the kind of, we know our algorithm doesn't perform too well on those. And in that case, your question about the last unopened question, where it's in the constraint satisfaction problem, how do you model rows/columns that consist of multiple words with different clues? For those kinds of clues, we would say that would be a future work or improvement we would have to do. There are many kinds of clues that we would probably find a little difficulty with trying to catch. Certain examples is, for example, we get like an abbreviation, for example. That's one example. We would have to either reparse. We would take the abbreviated word and say, okay, this actually is an abbreviation of this word, and count that as that word instead. Or some clues that are like nonsense words, like that you would never find in a dictionary or typically. One example I could think of is what is like a date format? And the answer would be like MMDDYYYY. That's not something you would typically see in like a dictionary or in the kinds of databases that would hold just information like that. So I guess in our case, we have no model for that now, but it is certainly an improvement that we can try to work on in the future.
All right, well, thank you all very much. I think we'll transition to our next presentation. So if I could have the panelists for the next session, Gavin, Angie, Andrew, and Isaiah sign on. Excellent.
Awesome.
And who is presenting?
I will be presenting.
All right.
We all good to go?
I believe so, yes. As a quick reminder for those of you who joined late, this is the Whitman Computer Science Capstone Conference, the virtual replacement for our sessions that we would have conducted at the Whitman Undergraduate Conference. These sessions are being recorded to post along with the Whitman Undergraduate Conference proceedings, and we're very glad to have you all here. If you have any questions, feel free to enter them into the Q&A feature, and we'll moderate and get towards those at the end of the presentation. All right, so take it away.
Awesome. Thank you so much to everyone for coming and watching the presentation and supporting all of us. My name is Andrew Harvey. I'll be presenting today with Isaiah Banta, Gavin James-Beckham, and Angie Mead, and we are part of the Autotuners group. There we go. All right, so quick little description of our project. We created a web application using the fast Fourier transform, we'll be calling that the FFT from here on out, in order to shift the pitch of a sound file. So we made a user interface that allows a user to upload a sound file, select the number of semitones and octaves that they want to shift their file by, and then play back their new sound file once we've completed the auto-tuning process in the back end. In this presentation, we'll run over how the human ear interprets sound and the way it's similar to the FFT and how we use that to our advantage, the algorithmic steps taken to solve this problem, and a one-time only, never before seen live demo in the quarantine of our project. And then lastly, we'll run over some challenges and obstacles that we experienced along the way. But first, I'm going to talk a little bit about a naive approach to pitch shifting. So you can very easily just speed up a sound file. If you've fast forwarded a movie, or if you've used that Snapchat filter that has the rabbit on it, you've all heard what it sounds like when you speed up a sound. Right here, we have a graph that is taken from Angie, my group mate, singing an A440 note. If we wanted to change the frequency or the pitch of this, it'd be really easy. We could compress it. The samples per second would increase and then the pitch would be higher. However, this method doesn't allow us to manipulate pitch and speed independently, and that is what brought us to the FFT. It allows us to split those two parts up and then synthesize them back together, and so we will be discussing that through the rest of the presentation.
Yeah, so now that we've covered what the naive approach to pitch shifting would be, and later we're going to cover the way that we implement the FFT to address that. Let's talk about the comparison to the way that the human ear identifies pitch. So on the left, you'll see an image of the ear canal. And as you go on through the ear in this spiral cone, it detects lower and lower pitches. And so you kind of see the spiral of the ear elongated and in a line on the right-hand image. And so the way that the human ear identifies pitch is that there are small little hairs inside the ear canal, and the way that the pitch goes in into the ear when we listen to it is that the specific pitch will make the ears, this is a very basic description, vibrate, and then we'll be able to identify certain pitches based on which hairs vibrate. And that's actually pretty similar to our FFT algorithm and our phase vocoder algorithm that we use to identify the pitches. So if we can go to the next slide. So on the left, we have the the A440, which is the A just below middle C on a piano. And then on the right, after we've ran it through our fast Fourier transform, our FFT, we have individual buckets that will identify where the pitch, which frequency the pitch is. And so here we can see that we have a really large bucket in this area, which gets the A sound. And the issue that comes up with pitch shifting and auto-tuning that the fast Fourier transform addresses is if you have a complex sound as opposed to just one note, as we have on the left-hand side, that combines multiple notes or a chord, and how do you distinguish one note from the other? And also after that, how do you apply the pitch shifting to each individual note in a way that doesn't distort the sound, because you have to do it as a ratio of the frequency of each note, as opposed, you can't just do it all across the board to the chord. So the first problem that needs to be solved is you need to decompose each of the waves of the sound, each of the individual notes that make up the complex wave of the sound. So instead of a simple sine wave, you would have a complex wave that would be much harder to decompose. The fast Fourier transform allows us to do that, and then allows us to apply our auto-tuning, whether we want to raise it by a certain amount of semitones or lower it by a certain amount of octaves, whatever combination we want to do. And then we combine those waves into its complex form again, its new complex form, with the inverse Fourier transform. And that process will be covered a little bit later.
One cool way to think about it is like if we had a bucket of purple paint and we were trying to figure out what paint was mixed to make the purple paint, the fast Fourier transform is letting us split up the red and the blue paint and figure out, oh, we had some red paint, we had some blue paint, and that mixed together to be purple paint. The fast Fourier transform just does that with the complex sounds that Isaiah was just discussing.
Yeah.
All right, so when we first read in the data from a wave file, it comes in the form of an array of real numbers. So the first thing we've got to do to it is window it into a bunch of overlapping chunks. So we end up with an array of arrays of real numbers. And windowing the function allows us to get the frequency information from distinct points in time in the audio file rather than from the whole audio file at once, where it would just end up as a jumbled mess and you wouldn't know at what time the frequencies go where. Having the windows overlap also helps keep the signal smooth after we take the Fourier transform of it, and it helps prevent spectral leakage, which is essentially when the Fourier transform says that there are pitches that aren't actually in the audio file because of how the wave is lining up with your windowed buckets. So this image here on the slide hopefully helps illustrate how the windowing of the array occurs. The x-axis of the graph would just correspond to the array of real numbers that we get from the wave file when we first load in the data. And then each window, in this case of length n, in between the arrows, you can see it encapsulates all of the data from the original array. There is some data duplication in the overlaps. In this image, the windows are overlapping by 50%, which is the same we used in our project. So then step 2, we've got our list of lists of windows. And so we can take the FFT of each window. And so we get transformed from the time domain. Now we're in the frequency domain. And then step 3. So now that we're in the frequency domain, we want to find out what are the fundamental tones at those distinct times that the windows correspond to. So we do this by detecting the peaks for each window. And we defined a peak to be any index that contains a greater value than its 3 closest neighbors, both to the left and to the right. And then we end up using the peak indices to calculate how much we should shift entire regions of influence around the peak. And so a region of influence is a range around each peak that starts at the index with the minimum value between the previous peak and the current peak, and it ends at the index of the minimum value between the current peak and the next peak. And so we want to shift these entire regions by the same value because of how not all frequencies are going to line up perfectly with our window. So you might have more than a full period of one wave, and it'll be spread across multiple indices when it's just one wave that we're trying to adjust. So then once we've got our peaks, we can actually shift the pitch. So for each region, we calculate the integer value that we can shift the indices by based off of the peak of each region. And then we move the values by either adding or subtracting to the index, depending on whether we want to shift the pitch up or shift the pitch down. So then once we've shifted the pitch, we essentially just want to reverse all of the stuff we just did to get back to the time domain. And so we run the inverse Fourier transform on all of the windows, and then we can recombine the windows by adding the indices that correspond to each other in the overlapping windows to get an array back of the original size that we read in. And then we can write that out to a wave file, and it's ready to play. So I know that previous slide's a bit dense, so we just have this one to kind of clarify what's going on. This flow diagram just reiterates the basic process of our algorithm. So on the left side, you can see in the red bubbles that that's where we're in the time domain. And then on the right side, that's where we're working with frequency in the frequency domain in our arrays. So at the start in the top left here, we just upload a wave file, open it, and then we window that array into a list of lists. And then we take the FFT of each of those lists in our list. And then we find our peaks and our regions of influence for all of those windows individually. And then we go down to the second row here on the right. We shift the pitch according to the shift factor that we calculated from the peaks, and we shift those regions independently from one another. And then for each of those windows, we're going to take the inverse Fourier transform, and then we're back in the time domain here, so we can combine our windows, and then we've got a final array here that we can write to a wave file or play.
All right, I'm going to stop sharing so Angie can take over.
All right, so it is time for our live demo. So our first step is to upload a file. I'm going to upload my tetris.wave file and submit that. And then we can choose it from our drop-down menu here. And I'm going to shift it by 3 semitones and 1 octave, and the name of my new file will be Now, one problem we ran into in this program is that our backend code takes a while to run. We think this is because we stored our data as a NumPy array, but then iterated through it as though it were a Python list, which may be the reason it's slower. But while that's working, we can hear our original file for comparison. All right, and now hopefully it has worked. It has not worked yet, so we'll keep waiting. Oh, now it works. All right. All right, so that's our application.
All righty, I'll take it back for the rest of the presentation. If this slide wants to change, we're going to discuss some of the challenges that we've faced. Maybe. Slide doesn't want to change. Sorry about that. There we go.
Yeah, so There were some tricky challenges at the outset with the way that we were reading the research papers. And so to start off our project, we needed to get a basic understanding of how the fast Fourier transform works and what it would need as an input, what it would output, the process of auto-tuning, and why it's like a problem that needs to be addressed in this way. And that was initially a learning curve to have a lot of new language. Also, some of the research papers used different phrasing for the same thing. So before, you have windows or you have buckets, and then the smoothing function that we added to reduce the edges, people use different forms of that, sometimes for different cases. So sometimes if your audio pattern is slightly different, you might benefit from a different smoothing function. And so parsing through all of that was challenging because it was a lot of our first time really delving into research in this way, and it took a lot of very close reading. But eventually we were able to figure out more what was going on. There was some helpful research papers that were more modeled towards like being a tutorial into the subject. And also there were some really useful YouTube videos that we were able to watch of more the math side of the fast Fourier transform and the ways that it's applied in many other areas other than audio. And then after we kind of got through that, we were, it was the challenge of choosing libraries and tools. And I'll let you talk about that.
Yeah, so this was really difficult because we had a very open-ended project. We were, would C++ or Python be a better language, but we don't know whether we're going to care about performance or if we're going to care about front-end stuff. So there was lots of difficulties with choosing those. We settled on Python and NumPy to write all of our code in because we've used it a lot for our classes, and the four of us all had pretty good experience with Python, and NumPy seemed like a really good choice to manage our data. They had lots of built-in functions that would help us a lot. On the front end, we chose to use Angular and Django because Angie had a little bit of experience with those through one of her internships. This was probably the hardest part for us to get the ball rolling because we had 4 different personal machines that we were running this code on, and we had different libraries and dependencies installed in our 4 different machines. And so there was a bit of a learning curve to make sure we had everything installed correctly and that we were able to work on it at the same time. But once we got past that, those turned out to be great decisions, and those libraries and tools all had lots of functionality that helped us a lot throughout the project. Isaiah, do you want to touch on the last one?
Sure. So the next challenge that we had was using those libraries to implement the phase vocoder algorithm. And so that's the official name of the pitch shifting. And so one of the things was choosing a windowing function. And so, as I said earlier, there's one called the Hamming window, which is the one that's generally considered to be the best for all of the cases. But we actually got similar performance from just using a simple like cosine smoothing smoothing function for our windows. And we think that if we did more work on the vocoder algorithm, that we would then experiment more with different smoothing options for our windows. And so a lot of this was implemented by doing going back to new research papers and seeing the different ways that they implemented it. And that was another difficult portion, is that there's so much research in this area that there isn't really a clear sense of like one right way to do it and a wrong way to do it. There's many different ways of doing this. And so when we would jump from one research paper to another to kind of get more information on how to carry this through, not only would the language be different of the ways that it would be applied, but it would also be different in their method. And so figuring out which pieces of that we were going to transfer over and use in our code, or what we were going to use as information to not do in our code, was a challenge. And we ended up benefiting a lot from identifying one specific paper that was able to show a more challenging piece of the phase vocoder algorithm, which was the specific phase shifting of the various pitches that we would, once the FFT has been applied.
And so that brings us pretty nicely into the next steps for this project, or maybe more accurately, things we wish we had time to work on. And as Isaiah talked about, one of those is experimenting with various smoothing functions for our windows. We settled on using just a very simple cosine window, but the Hanning window is the one that we saw the most in the literature and that we wish we could have experimented with more. We also wish that we could have had pitch shifting be dictated by the melody of the song. So imagine that you sing into the microphone and then say, I want my singing to sound exactly along the melody of Happy Birthday or the ABCs or something. So the one challenge with that we didn't have time to work on is the pitch detection part of it, and then translating that into the number of semitones that we would need it to be shifted. Lastly, the one that we really thought we might be able to do, but was just a little bit too much for us, and Angie mentioned the speed part issues that we had, is live auto tuning as opposed to having a user upload a pre-recorded file. That would have just been a lot more fun to be able to sing straight into your phone and then have the outputted sound be auto tuned. But like I said, it was just a little bit too much for us to handle in the time that we had on the project. And so that brings us to the end of our presentation. Thank you guys very much. All right.
Great, thank you. We have a couple of questions that came in. So one was, someone heard a rumor that your application could also speed up a sound file without changing the pitch. Could you explain a little bit more how something like that would work?
Yeah. Andrew was talking about this at the beginning of the presentation, where a really easy way to shift the pitch of a sound file is just to play it faster. So you're just playing at a faster sample rate than it was recorded at. So it sounds as if you're crunching the wave together. So it sounds at a higher pitch if you're playing it faster. And the issue with this, of course, is that it's half as long if you play it twice as fast. So by separating the time information from the frequency information, once you have the pitch shifting working, the speed change is really easy. So if you're going to, if you want to play your file twice as fast, you just have to shift the pitch down an octave. So it's twice as low. The frequency is half. And then you play it twice as fast, and it's the same length, but the pitch has shifted. Or sorry, it plays faster, but the pitch is the same.
Cool. And another question was, you touched on this a little bit, but what choices did you make that you think might have affected the speed or the performance of your implementation? And if you happened to start everything over again and wanted to, apply things that you've learned from your first implementation, how would you make those choices differently if performance were something that you wanted to improve?
So the reason why our algorithm is so slow is that for every single window in our array, we have another for loop going through every single item in that. And we're not making use of NumPy's built-in vectorization capabilities. Yeah, it was unfortunate that we had to do this. It pretty much came down to a time issue where we were having a lot of trouble with unwrapping the phase or wrapping the phase properly so that there wasn't a bunch of stuttering in our final sound file. And it just required a lot of experimentation with specifically what we were doing to each index. And we just didn't end up having time to refine that better to make use of NumPy's vectorization. So if we were to go back again with what we know now, that's definitely the first thing we would do to optimize it, is just make sure that we could do multiple operations on the array at once rather than going through for each item.
Cool. Well, if there are no other questions for now, thank you all very much again. And I'd like to invite up the next group on automated mentor-mentee matching.
Hello, everyone.
You ready to start? Okay, so thank you everyone for coming to our presentation. We are the Mentor Frame, and we've been working with the Student Engagement Center on one of the community service programs, specifically the Whitman Mentor Program. And a little bit about the program. The Whitman Mentor Program serves to build strong and lasting mentor-mentee relationships between Whitman students and young people from Walla Walla elementary schools. Whitman students join their mentee at recess once a week to build a healthy relationship and have fun. So a little bit about the process. So what they've been doing is they've had intervention specialists at the elementary schools who complete paper surveys recommending students to be mentees in the program. And then we have Whitman students who complete a Google form with the information on availability, transport, gender, age preferences, language, and any special considerations they might need. And then finally, the mentor program interns match mentors and mentees by hand. And this is usually in 3 categories. There's returning students, who are basically students that have participated in the program before and are most likely to be paired with mentees that they've worked with before. And then we have walkers and bikers who go to nearby schools. And then we have drivers and carpoolers that go to schools that are farther away. So our objectives for this project were 1, to revise mentor and mentee forms. 2nd, to account for open-ended questions so they can allow for some manual matching. So for example, if say a mentee has some special considerations that we didn't take into account when we were doing the matching process, that the interns can be able to do that matching. And then automate the matching process, which was a big part of the project because the interns are spending a lot of time doing this matching process by hand. And this saves them a lot of time so they can focus on other parts of the program. Then we developed a carpooling and transportation groups, taking into account the distance to schools. And for those who cannot be put in a carpool, being able to put them in a group that will take the community service van. And then another objective was to generate usable output that indicates, the carpools, the people who've not been matched, the people who need to go into the community service van, so that if the interns need to move anything around, they have all that information in a usable form. And then finally, we needed to maintain the privacy and of mentors and mentees. This was really important. Next slide. Implementation. So first, we built a list of all potential mentors and mentee pairs. And some of the questions that we took into account were, do their times match? Do their gender preferences match? Are the language needs of the mentee being met? Does the mentor have transportation method? And do they share common interests? Then next, we run this output through a bipartite matching algorithm, which we'll talk about later. And the point of this was to produce the maximum amount of matches. And then finally, we use a backtracking algorithm to create carpools. Challenges. One of the challenges we faced was the format of the forms that we needed to use. So first of all, the mentee forms were paper. Like I mentioned, the intervention specialist would do that. It was a physical form. So we needed to change that into a digital form. And then for the mentor form, we also had to move or modify some of the questions so that the output was usable for our algorithms. The next thing was transportation. So it was really important to make sure that everybody got transportation. So for example, if we were to match somebody with a mentee at a faraway school, it was really important that they would be able to get into a carpool. And that was a bit challenging to be able to verify that. And then time ranges. So the times listed in the mentor form did not exactly line up with the lunch times at the schools. So we had to find a way to work around that. And then the last one is preferential matching. We couldn't take into account all of the preferences of the mentees and the mentors. So for example, we didn't take into account hobbies and similar interests. Instead, we focused on availability, gender, language, and transportation preferences for algorithms.
Yeah, so kind of like Biaki kind of mentioned before, one of the first things we had to do on the technical side was pre-matching, which is basically we had to build a list of potential matches. And the first step to that was, what will be shown later on, is we have to first convert form responses to a spreadsheet. So the mentors or the volunteers fill out a form that then gets sent to a spreadsheet, which we then use as our database. And we then parse that spreadsheet for information. And then the third step is we remove the returning mentors and mentees, because no matter what, the mentors and mentees who are returning and were matched last year, the community service interns have tried to match them regardless of availability. So we just remove them from kind of the whole pile, and we try to match them together again for the next year. And the last step is just to find all the potential matches for the rest of the mentors and mentees. So this is kind of what the form looks like. Each question is essentially a column in the spreadsheet, which I'll show next, and each answer goes down in that column for each person. So this is an example of what the spreadsheet will look like after we download all the forms, after all the mentors fill out all the questions on the form. So basically, if one person fill out the whole form, this would be their name and then their gender, and so on for each question. So the way, the first thing to think about is how we would store information for each mentor and each mentee for easier access. And the way we went about that was we used object-oriented programming. And I'm just going to do a basic breakdown in terms of how we use that for this specific project. So we have two classes, one for the mentor and mentee. And for each mentor and mentee, we have different things that we wanted to know about them and that we wanted to kind of store for later when, for say matching, or even for this section of pre-matching. So the result of that will essentially look like this, where you have one mentor, and inside that mentor, you could access anything you want to know about him when it comes to transportation, gender, language abilities, or anything else that we needed that we thought was important for this stage of pre-matching or for later stages. So continue on from that train of thought. For the mentors, we decided that the name was really important to remember the gender, because the mentees might have a gender preference for their mentor. Language abilities, can they speak Spanish or not? Transportation, for the cases where if the school was too far and you needed a car to reasonably get there on time, we need to know whether or not they could make it in a car, or whether or not they're willing to carpool with other people to get to a school far away. And also if they could drive the community service van, in case one person maybe didn't have a car, but they could drive the van with other people, and we would know then that that amount of people could go to this, a distance school at that point in time. And of course, time availability was important. We had to know that they had enough time to get to the school and spend a good amount of time with the mentee during their available time, so that that would all work out. For the mentees, it was basically a similar, kind of similar requirements that we wanted to look into. And for their time availability was kind of just lunch. So we kind of had to match up for each mentee what their lunchtime was, and we had to see whether or not the mentor's time availability could match any of the mentees' lunch times. So then the results pre-matching basically ended up something like this, where it's kind of an extension of the last example I showed you, where you have still the mentor, you have still knowledge about the mentor's transportation, language, gender, etc. But now you also have all their eligible matches. So kind of like what Charlie was talking about in the matching stage, you now know kind of what each mentor can possibly be matched with. And now the next step, all we have to do is figure out who to match them with to get the most possible amount of matches.
Yeah, so as Robert had mentioned, after we've made all these original setup between the mentors and mentees, then we actually go into the matching phase of the process. Next slide. And yeah, so this is kind of the way it's being represented. So you're looking at it as if it's a graph where you have two columns of nodes, on the left being mentors, on the right being mentees, and the connections between them is whether or not that mentor can be matched with that specific mentee. So as you can see in this is a simple example, but each mentor could be matched to a number of different mentees, and each mentee could be matched to a number of different mentors, meaning they potentially could be matched at the end of this process. Next slide. So when you're going through and you're doing a matching, and this is how it would be done manually as well, you're gonna go down, you're gonna just go down this list and make these matches. Eventually, as you can see on this third graph here, you're gonna hit these conflicts where you've already matched that person, and all of a sudden you have a issue there with that specific node where they don't have somebody that they can match to. And again, we're looking at a set of 4 mentors and 4 mentees, but in an actual data set where we're looking at closer to 60 to 80 mentor-mentee combos, this process can become very complicated, and that's part of the difficulty of actually going through a matching, is being able to correct when you hit issues like this. So next slide. So then, so as been mentioned, we wrote a bipartite matching algorithm, and basically it follows that same principle where we're going through and one by one we're creating a match between a mentor and a mentee. And then as you can see by the node highlighted in green there, we're going to hit that same issue as before. But part of the step of matching that mentor to a mentee is going to involve going back through and as you can see in the second graph here, we need to go back through, we're going to go up to the previous mentor, and we need to make a correction and look at the different possibilities of that mentor, so the other mentees that it could have potentially been matched with, and make those changes before we can go ahead and actually make a match for the mentor of interest. So this can be done. This isn't just necessarily referring to the previous mentor, but this could go back down the chain to eventually maybe change a handful of matches to be able to finally match the maximum amount of mentors that we can. So as you can see in the final graph here, we were able to match everybody by making these changes. Next slide. So at the end of this matching, we finally have an output where this is going to be a new table, and in that you can see the mentor and mentee combos, you can see the school that they're supposed to go to, and then a list of the days of the week and the time that they could actually meet up. And as Robert had mentioned, other information about the mentor that will be used later in the process, such as whether or not they're a driver and whether or not they need a ride. And that leads us into our next step of transportation.
Okay, so transportation was the last piece of the project, and we had 2 main goals for this piece. The first one is was to group mentors into couples based on their schools and the times they were available. And the second one was to create new sheets for the couples generated, the leftover mentors with cars and leftover mentors without cars. Next slide. So we used a backtracking algorithm, which is basically a technique that incrementally builds candidates to a solution and abandons each partial candidate or backtracks as soon as it determines that that candidate cannot possibly be completed to a valid solution. So for those of you that are familiar with a game like Sudoku, when you fill in a digit and realize it's not leading to a solution, then you remove it and try another digit. So it's basically the same concept of backtracking. Next slide. Okay, so we used match objects for our main function. And this was basically the first 5 fields: the mentor name, mentee name, school, needs ride, and is driver. This was output from the previous section that Charlie talked about. And then we added 2 other fields, which is the availability object and count. So the availability object was used to find intersections between mentors based on the times that are available. So looking at 2 mentors and the times that say they're available throughout the week, can we find a time that works for both of them? And then the count was used to order drivers and riders by constraint. And this was a decision we made so that we build our couples around the most constrained drivers and riders, because if somebody only has 1 availability throughout the week, then we want to definitely get them into a couple, as compared to somebody who has like 3 or 4 options. They will most probably land into a couple anyway. Next slide. Okay, so for the function, the couples function, it takes a list of riders and a list of drivers, both ordered by constraint, like I mentioned. And first we remove the unassignable riders from the list and put them into another list. And when I say unassignable riders here, I mean riders who do not have compatible drivers. Like, we've looked at the list of all the drivers and there's no driver whose time matches with this rider at all. And then, so we put that into another list that we'll use later. And then using the list of drivers and riders left, we add people into carpools. So looking at their times and schools, we add them into a carpool with a driver and up to 3 riders. And once we make a couple, we check to see if it leads to a solution. If not, we undo it and try a different couple. So this is where the backtracking comes in. And then once we have like the best solution, best couples, we add those couples into a list and return that list. And finally, we output them into the different sheets that I talked about at the beginning of this section. So now we'll move into a live demonstration.
So basically, we're going to give you a demo of what we have so far, and it's not perfect yet, but it will show all the different components. And so basically how we use Google Sheets, and then having different buttons that you can press within the Google Sheets with the informations about the mentors and the mentee. Okay, great. So this is an example of a mentor sheet. And so if you can navigate through on the bottom tabs. So this is a mentor sheet. And then would you go to the second tab? That shows information about the mentees. So they would have, we've obviously taken away for privacy reasons, but they would have all the information there. And then the next tab has the lunch times. And so we thought that was really important to include this way instead of writing it directly into our program, because each year those lunch times might change. And so this allows we wrote our program so that the interns can just change the lunch times on here, and then based on these lunch times and the grades that each of the mentees are in, the program will adjust what time each of the mentees are available. So this makes it changeable and usable year to year, which we thought was really important. Okay, and then if you can press make matches up top. Yep. And so you can press that, and that runs the first part, which finds as many possible matches, which is the part that Robert was explaining.
and Charlie. Okay, so it'll run. Okay, and so this sheet will give an output if there's anyone who was returning, then those will appear on the separate sheet. And we thought that was really important so that the interns can just automatically see who's returning, because those people they try their hardest just to pair those people together no matter what. And then, and then if you click on matches, you can see a big sheet, and that just lists a mentor and a mentee and the overlapping time that they're available. And so you can also see if they have a car and if they need a ride and all that stuff through that sheet. So that will give the interns a lot of information all in one place about the matches that we made. And then finally, the part that Buyaki was explaining, making the carpools. So if you click make carpools, run that. Where the output is not exactly as we would expect for this one yet, and we're still kind of working on it. But this will give you the general idea of what it outputs. So if you keep going, then this creates the new carpools. And so you can have up to 4 people in each car, and it will automatically put people together. And then it will also say what time and what school they're at. And then, we'll also have a sheet that shows you the mentors with cars. And so that's important because then the interns can email these people and say, okay, you have a car, you'll just do your transportation on your own. And then the people without cars will be on another sheet. So you can click that. And so through there, the interns can go through and see who can ride the van. And this creates like the smallest list possible that they'll have to kind of manually match together. And so as you can see from the carpools, there wasn't that many. And that's because we only matched people whose times matched exactly. So if you were from 11:20 to 12:50, then you could only be matched with someone that was at exactly that time. But an extension of this project would be to add plus or 5 minutes on either side and see if carpools could kind of encompass a bigger group. And so that's definitely an extension of this project that we thought about but didn't have time because of time constraints. So that's a demonstration of our project. Yeah, and that's it. And if anyone has any questions, we'd be happy to answer.
Great. Thank you all very much. So one quick question I had was, how would you imagine this being extended? So obviously this is for the mentor matching program with the elementary schools in town, but are there, what other programs do you think might this kind of system be used for, and how would you imagine going about extending it so that you could have more programs be able to use this system?
Well, a lot of it is dependent on the columns that we're actually looking at of the specific sheet. So it's looking for a mentor name or a mentee name. So the change would be to make those inputs more general, where if you had a generalized structure for a form that similar programs would fill out, that it knows that it would be able to figure out what we're trying to match, even if it's not specifically referring to mentors, mentees.
Yeah, and so a lot of the other programs at the SEC, they put people together based on eligibility criteria. So as long as you understood what those criteria were, you'd be able to adapt it to another program with some changes, but that would definitely be pretty straightforward.
Mm-hmm. One question that came in was, what were some of the most challenging aspects of this project, either technical or non-technical?
I think a big problem we had was we had to kind of make our own decisions in terms of, like, one of the few things we talked about was preferences and what were the most crucial ones. And it kind of seemed like it was something we didn't expect. I think we kind of expected to, for like, I think we expected to spend far less time on making kind of just decisions in general about how we're going to approach things versus actually working on the technical aspect of the project. And I think we didn't see that coming, and that stalls a little bit. Just because more and more decisions have been coming up in terms of what we had to choose when it came to preferences, transportation, and all those other areas that we just talked about. So I think that was probably one of our biggest problems that we had to kind of overcome in the project there.
I think another challenge would be like technically, we did this code in Google Apps Script, and at the beginning of the project we had to decide what language to go with, and we decided to go with Google Apps Script because it worked well with the spreadsheets that the interns had been working with. One of the other alternatives that we thought about was using Python and creating like a standalone application, but then we decided to go with what was most comfortable for our client.
All right. Well, if there are no other immediate questions, thank you all very much. And I would like to call up the next group on great explorations, designing an algorithm to have a human touch.
Thank you.
Thank you.
All right.
All right. Are we all here? Ian, did you want to go ahead and bring up the share
I'm
screen?
here. Yep. Just a second.
Cool.
Yep.
Zhuang, do you have yourself unmuted there?
Yep. Yep.
Oh, there we go. Okay.
Perfect. Okay, think we're all good?
Yep.
So our team name is The Lads. My name is Isaiah Standard, and I'm joined by my teammates Chris Pyles, Ian Hawkins, and Trung Vu. We were the Capstone group tasked with developing a matching and scheduling algorithm for the local Great Explorations Workshop program, hosted here locally at Whitman College. So moving on to an overview for our presentation today. First things first, I'm going to fill you in with what Great Explorations is in the first place, and some brief history behind that. From that, I'm going to explain to you the main quote-unquote problem that we as a group work to provide a solution for. This is going to be followed by some of the groundwork that was already laid out for us by the previous year's Capstone group, who was tasked with a very similar project to what we were. We're then going to briefly review some of the client expectations and goals from the start of the project, as well as our workflow we use to help us achieve these goals. And then finally, following this is where we're going to be explaining the model we use for our solution, and we're going to dive in and break down the algorithm itself. Go ahead, next. And then moving on to Great Explorations. So Great Explorations, or GE as we referred to it, is a nonprofit STEM workshop hosted by Whitman College every other year. Their goal is to provide 5th through 8th grade girls with an informal, hands-on experience with careers that utilize science, technology, engineering, and math. Something special to note about the GE, or about GE, is the fact that it's all female ran. From the attendees to the workshop presenters to the keynote speakers and even volunteers. So that's something very special about it. It originally started back in 1984, where it welcomed 50 attendees its first year, and it has grown today to host around 450 girls in a variety of 30 different workshops. So where do we come in? The quote-unquote problem with the growing student numbers is that somehow 450 of them each have to be sorted into 3 of 30 different workshops. And this is all based on their top 6 workshop preferences that were given. Prior to last year, all of this was done by hand, which is kind of crazy to think about. But so you can kind of imagine all the time that can possibly be saved if we can automate this process. So some of our main priorities this year was to try to give each attendee 2 of their top 6 preferences. Also, each workshop was to be proportionally filled. So we landed around each workshop trying to have at least 75% filled minimum. Some of the popular ones obviously going to full capacity and so on. And finally, something that changed from last year's group to this year's is that we wanted our clients to be able to run our final project without any support from us after finally handing over to them.
So last year, Great Explorations partnered with another Capstone team, as we mentioned, to meet some of their essential requirements. That team built the Great Explorations website and also a basic version of the matching algorithm that we took on in this project. One thing that they did there is they built a Google form into the website, just embedded there, to handle signups. And they also chose to implement their algorithm in Google Apps Script, which let them read from the results of the sign-in form or the sign-up form without worrying about, APIs. And you don't have. Well, anyway, we'll get into the Google Apps Script choice. So we liked that solution. We liked the form, and we liked the choice of Google Apps Script for reasons that we'll talk about next.
So in choosing to inherit the Google Apps Script, we also the decision was made because it really streamlined the input and the output, because the input is based on a web form on a Google Answers, or so where they select where all the so when people register, when they pay and everything, they also select their 6 preferences, and then those entries are recorded onto a Google spreadsheet, which all of the input data for our algorithm is taken. Also, in terms of user interface, it didn't really require any installation of software, which just reduces the confusion for our client. Our clients are kind of are Carol and Ruth, and they're both they're not as technologically what's the word I'm looking for? Somebody help me out. As inclined as us computer science majors, so we wanted to make it as easy as possible. So all they have to do is pull up the document on on their Google Drive, and then just run the script, which is just from a pull down tab. So yeah, all these kind of decisions to inherit the previous work was also done in mind for just being user friendly. So, but yeah, and it was also easy because we could kind of do everything we needed to do without inheriting any other or having any additional libraries. So all of the things that we have was just done using the Scripts app. But there were some difficulties regarding using Google Scripts apps. There are a lot of features that we didn't need, and with JavaScript, because Google Apps is just JavaScript. There are a lot of problems such as classes. We kind of had to figure out a lot of workarounds. Since we couldn't use classes, we kind of just used functions. But yeah, if you go to the next slide, you can kind of see the registration form. The registration form is just they just pick. So for the input data, the students, along with a lot of personal information, would choose 6 preferences, and on these 6 preferences so each choice, so you choose from 30 workshops and 6 preferences. But there is a problem with the registration. Technically, the people who register could just all select the same workshop, so all their preferences be one workshop, or they could accidentally duplicate a choice, which we kind of considered in an algorithm. But yeah, from this form on, this is where we collect all the data that we need from the people who register, as well as the workshop information from that we get from the client. Okay. So in talking to our clients and what the focus of our algorithm should do, which is kind of an extension of what Isaiah talked about in the problem, we have to fill every workshop to a minimum certain threshold, or just like given like a certain ratio of students, each one has to be kind of filled proportionally to each workshop, because the client didn't really want, like, because all the people who came to and made all the effort to put together these workshops, they didn't want any of those people feeling like disrespected or kind of left out because no one preferenced their workshop, or their workshop wasn't as, you know, popularly requested. So that was kind of a priority for our client to make sure that every workshop was filled. But given this limitation, we also had to make sure that every student at least receives 2 of the workshops in the preference list. We recognized early on that this could be kind of a problem depending on the distribution of how the preferences are, because, you know, with people from 5th to 8th grade, or how the workshop is listed or marketed on the form or on the website, there are going to be, you know, some workshops that are really popular than others. So I mean, there, you know, there could be problems, because like, what if, you know, all the students preference all the same 10 workshops, and like all the other workshops have like 0 preferences. And so that way, you know, given certain data sets, that this this requirement could be difficult. But running our algorithm on the current on previous years' input data, we didn't really see any problems, because preferences were distributedly even enough for kind of for this condition to be met. They also wanted us to support pre-assignments, and I'm going to elaborate that. And like, so some students, you know, with certain conditions maybe, or they just want to be able to like select, they would want to be able to at least put some students in automatically within their workshops. So we found a solution to this by just kind of giving the design of the algorithm just by, you know, taking this as a separate input and just filling those workshop slots before the matching is done. And so we also needed to perform 2 rounds of matching. So after like this was done because generally when the matching is done, our clients will, like, through experience, have had, in their experience running this workshop, they understand that like they're going to receive a lot of the applications after the matching is done or after the schedules are set. So they wanted to be able to accommodate all of the people who registered afterwards, and try to like give them slots, or have it easier for them to like give them slots in workshops after everything is fine, after a schedule has been finalized. And yeah.
So we built our workflow in ways that were meant to help us maintain code quality and good velocity throughout the project. We made heavy use of GitHub's issue tickets for documenting our progress and keeping track of the state of things. And we also we really took advantage of pull requests as a serious opportunity for ensuring code quality, as opposed to, you know, trivially merging them. We really took advantage of one another's attention to improve our work. We also set up a couple of Git hooks that make the code adhere to style standards, and to warn of potentially problematic code before you can commit. So that helps us just maintain a similar standard across all of us. And then finally, we used some weekly meetings alternating between client and internal meetings, and we focused on deliverables and whatever, you know, what will we be bringing by next meeting, what will we have done, again, to maintain velocity. In order to model the relationship between students and the workshops to which they're assigned, we used a class structure sort of like this. We mentioned earlier that we weren't able to use classes before the V8 migration, but we made it work by making JavaScript, well, not to get into the details, but by using JavaScript functions that return objects anyway. So basically functions exactly like classes. Here we use a matcher class, which kind of handles the operation itself, the act of matching, and it attends to these this large number of students and workshops. The student knows about workshops only as like it has 6 preferences for workshops, and that's their relationship. And then the matcher assigns students to sessions of a workshop, 3 of them, as we talked about earlier. And all of these classes we designed very deliberately to be independent from the input and output sheets. So all of this is, none of this is particularly tied into the Google Apps script environment. That part is just, the actual IO, the sheet, spreadsheet input and output is separate from this active modeling here.
So that brings us to our algorithm. So all of this put together, we have 2 parts of our algorithm overall. We have our matching algorithm and the scheduling algorithm. And while these work in conjunction with each other, we consider them separately, so for the sake of explanation. So how the matching algorithm works is, first we take our 30 workshops and we sort them by popularity. This goes from least to most popular, and the reason for that is so that we can start matching students to the least popular workshops and move up to the most popular ones. Now, how we define popularity is by the number of times that a student any student lists that workshop in their preferences. It doesn't matter if the workshop is listed as preference 1, preference 2, or preference 6, or anywhere in between. As long as it's listed once, that workshop gets 1 popularity point. So we get a number at the end of that indicates how many times this workshop was listed. The reason this is important is that some workshops don't have enough students who list them that prefer those workshops to reach their minimum value. And so in order to meet that, we need to make sure we know in advance that we're going to need to assign students who didn't list those workshops as preferences to those workshops in order to make them reach their quorum. This is our first stage in the workshop matching algorithm. So starting with the least popular workshop, we assign students who prefer that workshop until it's sufficiently filled. If we're unable to fill that workshop, then we choose students at random and assign them to that workshop. But because those students chosen at random don't prefer that workshop, it wasn't listed in their top 6, we also make sure that we compensate those students accordingly by giving them their highest available preference. This way, if a student is given a workshop that they didn't want to be in, then the polite thing to do is to make sure that that student gets one of their highest choices. So when available, they'll get their first choice. If that's already full, they'll get their second choice, etc. So that guarantees that they'll at least get one of their higher preferences. Also important to note is that each student can only be assigned to one workshop in this way, where they are randomly selected. Partially because there are only 3 workshop slots, so a student couldn't be given 2 random workshops and 2 workshops as compensation. But we also want to ensure that students are getting as many workshops in their preferences as possible. So if a student is chosen at random and the algorithm determines that they've already been given a workshop as filler, that student will be deselected and another student will be chosen to be given the workshop at random. Finally, once each workshop fills up this way, this moves from the least most popular to the most popular workshop. Once this is all done, there will be a select few students that will not have workshops assigned to them, but their preferences aren't necessarily full either, because the minimum fill and the maximum fill of each workshop are separate, so we still have slots where we can put the students. So each one of those students who still has remaining time slots open is given a random workshop or their highest preference workshop. Bless you. Each one of those students is given the highest preference workshop that they have possible. And you can go to the next slide. And so scheduling. So I've already talked about how we match students to workshops, but how do we incorporate the time slots into that? One thing that's really important is that we can only match a student to a workshop if they share a time available. Even if a student has some time slot available and the workshop is not full yet, then that student might still not be able to be matched to that workshop, because if the student has only, say, time slot 3 available, but that time slot is full in the workshop, we can't match that student to that workshop. So that's the first thing we do. Every time we think maybe we should match this student to this workshop, the algorithm decides whether or not that's possible. If it is possible, what we do is we attempt to put that student into the workshop's least full slot. This is for 2 reasons. One, so each workshop session, time slots 1, 2, and 3, are all sufficiently filled, and also to ensure that they're relatively evenly distributed. We wouldn't want time slot 1 being filled with 30 students while time slot 2 only has 10. By attempting to assign students to the least full session first, this helps evenly distribute the assignments overall. If, for whatever reason, a student needs to be assigned a workshop but cannot be given the least full session, then that student will be assigned the second least full session, and then in the worst case scenario, the third least full session. This is just to ensure that the algorithm keeps going and makes sure that students are being assigned workshops, but by prioritizing the assignment of the emptiest sessions first, we found that this would help mitigate the even distribution of students across time slots. Next slide. So how did this work? What were our results? So after running this algorithm and making tweaks to it where necessary, we found that almost all of our students were assigned 3 of their workshops that they listed out of their top 6 preferences. So most students got everything, not necessarily their top 3 choices, but all 3 of the workshops that they were assigned to were ones that they listed as they wanted. We also ensured, by guaranteeing that no student was randomly assigned to a workshop more than once, we were also able to ensure that each student received at least 2 workshops from their top 6 preferences. And finally, every workshop did reach its minimum threshold, which we originally chose as each workshop needs to be about 70% full, because this is the highest we could fill all of them, given the number of students and the number of total slots. But we also made sure that this number is adjustable, so that if we wanted to guarantee more students get their preferences, while some workshops wouldn't be as full, that is an option for our client. The runtime of this algorithm is only about a few seconds, which is great considering that doing this by hand and getting matches that are this good or better would take tens of hours. And so we considered this overall to be a success in designing an algorithm that would have a human touch and take care of this matching the same way, or at least as well as we could, as you would by hand. So yeah, that was our project. Anybody have any questions?
Yeah, so if anyone does have any questions, feel free to enter them into the Q&A channel. Also, I see that the Great Explorations organization team is among the attendees. You all can unmute yourselves if you had anything to say or mention as well. One of the questions that I had, either for the Great Explorations organizers or for the project group here, is obviously saving an amount of time is a significant benefit in and of itself, but is there more to just the organizers having 10 more hours in their lives than they otherwise would have, or what's sort of the benefit beyond just saving some number of hours of time?
Well, I could at least start on this, and perhaps the organizers have something to add. But when it takes less time to do the matching, this last year, for example, or this 2019, there were a number of late signups, and if it takes a certain amount of time to perform all the matching, those late signups are at risk of not being able to be included, not being able to be added with the rest. This by increasing the speed at which this is able to be done, there's an option to accommodate late signups better than one would otherwise be able to do.
So one question we had, it looks like your algorithm performs really well, at least with the data that's been given. Were there particular choices about the design or implementation of the algorithm or the system that were difficult to come up with?
Yeah, I can take this one. I think that one design choice that jumps out to me was, at one point in the algorithm, we knew that what we had to do was assign random students to the workshops that wouldn't have high enough popularity to reach their quorum. So we knew we would have to assign students to those workshops and compensate them. But the question was, what would we do next afterwards? Because if we were to fill all those workshops and all the workshops remaining had high enough popularity to be filled, how would we proceed with filling those? Would we try to assign students their highest preferences, which was one of the ideas we thought about proceeding with? Or should we continue to fill workshops the same way? Ultimately, we decided to continue filling workshops the same way because there were some algorithmic problems that we figured would get in the way of trying to give students their highest preferences or fill up the students first rather than the workshops. And we decided that, because one of these, for example, was that if a student was assigned 3 workshops, should their remaining workshops that they listed in their preferences continue to count towards popularity of other workshops? Because that student can no longer be assigned to those other workshops, it shouldn't really count towards that workshop's popularity. And then there was the risk of a workshop's popularity dropping below its quorum, or not being able to be filled if too many students who preferred it weren't given that workshop. So we decided it was best to focus on filling the workshops with the students who preferred them, rather than giving the students their highest preferred workshops. And thank you, Carol and Ruth. It was fantastic to work with you on this.
Yeah, thank you.
Any other questions?
All right. If there are no other specific questions for the project group, thank you all very much for your work. And I would like to invite up our final panelists to present their work on data analysis of hybrid monkeyflower petals images.
All right, thank you.
Hello.
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 Since we are technically ahead of schedule, let's wait just a minute or two in case there's anyone signing on that specifically wanted to see your first 2 slides.
Sure.
And as a reminder for everyone who might be signing in now, this is the last presentation of our Whitman Computer Science Capstone Conference, our virtual replacement for the live Whitman undergraduate conference that was canceled. We are recording these sessions so that we can post the recordings as our contribution to the digital Whitman undergraduate conference as well. So we're very thankful for the opportunity to share with a live audience using this platform, and thank you all for coming in to support our students and our projects. So. Who's going to be presenting?
I'll be presenting.
Okay, why don't you go ahead and start sharing the screen and get that started?
Sounds good. Look good?
Yes.
Looks like a beautiful picture of a flower.
All right. Just let me know when you're ready, Sheldon.
It is 3 p.m., so you can go ahead and get started.
Sounds good. Hello all, my name is Owen Davis Bauer, and presenting with me are Jack Taylor and Abby Felley. And we're going to be presenting on our data analysis of hybrid monkeyflower images. So just a little bit of background before we dive into this. We were collaborating on this project with Dr. Cooley of Whitman's biology department and Dr. Prusi of the College of William and Mary. And they have ongoing research where they've been crossbreeding 2 different species of monkeyflowers, which you can see at the bottom of the screen here. And their goal has been to study the spotting patterns that form on the petals of the hybrid flowers that you can see in the middle. So their hypothesis is based on the idea of discrete spotting events to explain the spotting patterns, meaning that each spot comes from a discrete event that starts at the middle of the spot and extrudes outwards. So they're interested in the number, size, and location of these spotting events on the petals. And they already had a data collection pipeline in place for this that works pretty well, but it spans across both MATLAB and Python and requires some manual correction for each spot image. So for our project, we were hoping to design some meaningful image processing and analysis tools to aid in their ongoing monkeyflower research. And some of our goals for this were to increase the data collection efficiency and accuracy and lower manual work and data collection, meaning that there's no need to go in and make manual corrections, as well as create a well-documented and easy to use pipeline in one technology, Python. And this is important because obviously we're not going to be able to continue working on this project after this year. So we wanted to leave it somewhere where they could make additions or changes in the future. So now Abby will be talking about the pre-processing of the images that we did before anything else.
Yeah, so we basically have 2 separate pipelines, but they since there's so much variety in the images that we got, There's some pre-processing that needs to happen before either of those pipelines can really get going. Here's a some of the differences between the images include different colors, different color spaces. Like some of them are in black and white, some of them are in full color. There are different size images. Some images have more than one petal per image, so here you can get an idea of the kind of variety that we deal with. So the first thing, or the first issue, is that we want to convert our images from color to black and white, partly because some of the images that we're going to compare to are in grayscale already, and partly because reducing the dimensionality of our image arrays from 3 to 1 reduces the amount of data that we have to analyze, and thus the amount of time that our algorithms take by quite a bit. We also, this is also why most image processing libraries use grayscale images, and we don't, yeah. Next slide. So between the petal images, there's not really a constant size because they've been taken by different labs and like with different cameras at different angles, or not at different angles, but at different distances. Because our image processing pipeline compares individual pixels, we need them to have about the same number of pixels. And again, we prefer to reduce the amount of data that we have to process in the interests of time. So we shrink the images. An important aspect of image resizing is that we want the aspect ratio to maintain the same, so we don't get this stretched out version that you see here. I think what we ended up doing is resizing one image to match the width of another image and just hoping that the height approximates to about the same, and it does work fairly well. Next slide. The final thing is these images with 3 petals per image. We built a tool that uses image segmentation to find the edges of the petal objects, and we use that to get all of the different petals in different images since we're studying them separately.
So now we're going to start talking about the spot detection pipeline. So this is similar to the pipeline that they already had in place. We decided to start from scratch and rewrite the pipeline from the beginning, just because, first of all, it taught us a lot about kind of everything going on throughout the process. And there were some things that we wanted to approach differently. So to talk about this, we have to talk about what we call spotting events. And here's an example down here at the bottom of a spotting event. So these can be modeled as circles, starting in the middle and expanding outwards, like I've mentioned before. And this is very important when we get into our Gaussian mixture model, which is trying to predict exactly where these circles will be. And Jack will be talking about that later. Our current understanding is that the spotting patterns form somewhat randomly. On the right side, you can see 2 different spotting patterns, which are obviously very different. And what the biologists are interested in learning is how and why these spots form where they're forming. So to do spot detection, we're trying to look at an image of a petal and pick out every place where a spotting event occurs. So in a perfect scenario, this is kind of what we would look for as an outcome, where each of these spots are being approximated by a spotting event with a size and location. But obviously this is a more difficult task than just looking at the image and picking out the spotting events. So some of our challenges were overlapping spots, where, as you can see here, we have multiple spots overlapping each other that can't just be approximated by one single spotting event. And there's some ambiguity, right, between how the subspots are going to make up that larger spot. And there are a number of ways this could go. Another challenge that we dealt with is spots on the edge of the petal. And this is something that the biologists were previously treating as a spot that was centered right on the edge and would just expand outwards to whatever the radius of the spot was. But this was a tricky thing for us to do, and we didn't get as close to this as we would like to, just because it would require knowing exactly where the edge is, which is something we could add in the future.
All right, so the solution to the spot detection problem pipeline has 3 main components that chain together to find the spots. The first is a technique called principal component analysis, and we then use the results of that to create a spatial data scatter plot, which we can feed into our Gaussian mixture model and use to find the spots. So here's the image that we're going to be following along the pipeline. So the first step is principal component analysis. So the graph here represents the pixels of the previous image, but just charted in 3D color space, so you can see that they're all kind of floating in there. Principal component analysis allows us to find the axis for the data that will preserve the largest amount of variance, and the second largest amount of variance that's orthogonal to the first, which we don't need to get into. So so the first principal component is that longest line that I've drawn on there. And basically what we're going to do is we're going to use that to convert our image to grayscale in a way that preserves more variance of the data by projecting all of the data onto that line, essentially just finding the point on the line that's the closest to a given data point and assigning it to that point instead. We'll see what that looks like on the next slide. So on the left, we have just the grayscale image that's produced by the normal conversion function. If you remember that box from earlier, this is the grayscale image that you get if you projected it along that middle axis. But when we project it on our better axis, we get the image on the right. And you can see that it maps the palest colors in the image to white and the darkest colors to gray, even though the normal grayscale conversion algorithm would just map them all to sort of brownish. And this makes a much clearer image. So now that we've converted it to grayscale, each of the pixels is just represented by one number, and we use that number to represent the image as a scatter plot of spatial data points. So first we threshold out all the points that are not red, since basically all the darkest pixels will have the highest grayscale values or the lowest. So we just take away all of the ones that are below that and keep all the ones that are above that. And then we also use that number as the number of scatter plot points at the position. So that enables us to preserve some of the depth of color that you get in the middle of the spots as point density. And that allows us to use the Gaussian mixture model, which Jack will explain.
Okay, so obviously like the biggest part of this pipeline is creating circles that we can put on top of our various data plots, so that way we can determine where the spotting events are happening. And to do so, we use something called a Gaussian mixture model. Without going too much into the math of how those work, a Gaussian mixture model is a probability density function that is composed of many individual Gaussian distributions. And those Gaussian distributions for our purposes will represent these circles that we are trying to find. And the reason we use a Gaussian mixture model is because we can change the size and location of Gaussians really easily. As you can see by this graph on the side, using different parameter values for mu and sigma square really changes how the Gaussians will look in terms of their general location and their width, which is really good for us because we'll have a lot of different size circles, obviously in a bunch of different areas. So what we want to be able to do then is find the appropriate parameters to best fit our data with these Gaussians. But first, there is an important thing to be explained. Obviously, those bell-shaped curves that you just saw, those are not circles. So you're probably wondering how those will represent our circles. And essentially, the thing is with those Gaussians before, they were plotted over one-dimensional data across a line and fitted to data like that. However, our data is spatial, so it's across 2 dimensions, the x and y direction. So therefore, our Gaussians will actually be in 3 dimensionals rather than 2 dimensions. And so you can visualize this as before we had those bell-shaped curves. If you were to rotate those around and create a shell of the shape, you'd get this 3D thimble-shaped sort of thing, as you can see in the bottom right here. And then if you were to look at that from the top down, which we're trying to do with our x, y dimensions anyway, you will in fact get circles like you see on the left here. And so because of that, what we're really trying to do is we're trying to figure out how we can center those circles and determine their width so they will best fit our data. And to do that, we will use an algorithm that is called the expectation maximization, or EM algorithm. The way this works is we're going to start by randomly placing some number of Gaussians on our scatter plot. And then we're going to iterate through the following 2 steps. First, we're going to estimate how well our Gaussians fit our data. And then we are going to change the parameters of our Gaussians so that way they better model that probability of how well they're fitting the data to better fit the data. And on the right, you can see graphically kind of how this algorithm will work. The first picture is the initialization step where we kind of randomly place our Gaussians. In this case, we have 2 Gaussians, one that's yellow and one that's blue. And you can see the data points across the line are shaded differently of yellow and blue to show how much they are a part of each of the 2 distributions. The ones that are closer to the yellow that will have more yellow, and the ones that are closer to the blue will have more blue. And obviously in this first image, a lot of the points are just not covered by the Gaussians at all, which is why we then reparameterize them accordingly, which we can see in the second image. The Gaussians there are fitting the data a lot better. However, they are still not fitting the data great by any means. There are a few points, in particular x2 you can see, just kind of falls at the tail end of both Gaussians, which is not something that we want because it's not really covered by either of them. So that's why we repeat those second 2 steps, because in the third iteration, you can see that both Gaussians now cover the points a lot better. And ideally, we'll keep doing this process until we reach something called convergence, which is where every iteration after that will be the same parameters as our current iteration. And when we have that happen, that's when we know that we have the best fit for our data. But with using an algorithm like this comes a lot of trade-offs in terms of performance versus accuracy. In general, the concept is if you're working with a few things, then you don't have to perform as many operations, so your program will work a lot faster. But if you're working with a lot of things, you're not generalizing the problem as much, so you'll get a lot more accurate results. And some situations where we see this affect our algorithm is first with the number of iterations that we run. As I mentioned, we have to keep iterating ideally until we hit convergence. But sometimes that takes a lot longer, and we might get a decent approximation anyway with fewer iterations. And the less iterations you do, obviously, the faster you'll hit results. So that's pretty nice. The second one is image size. From the earlier images, you could see that you'd have some large blotches of points kind of close to smaller blotches of points. And by the nature of the probability distributions, when there isn't that much distance between those two blotches, the smaller one is just going to be absorbed into the Gaussians of the bigger one, which we don't want because we don't really want any of the white space to be modeled by the Gaussians. So when we have bigger images, the distance between each blob is actually further, so we don't have that issue as much. But with bigger images as well, we need to process a lot more data, which will take a lot longer. Similarly with point density, as Abby was talking about before, points that are much more pigmented, we want to give more density value to, because those points are more likely to be close to the center of a spotting event. And so when we're modeling our Gaussians off of that, it is very nice to be able to have those points matter more. However, the more points we put in one place is the more data we have to process through each iteration and calculate the probabilities for. So that will make it take longer, but again, will be more accurate. And here's a simple example of how that trade-off will work. On the left, we have an image that is 25 by 300, and on the right, we have an image that is 50 by 400. So the image on the right is bigger. And you can see that some of the circles, especially on the corners, actually do end up fitting the data somewhat better and like closer than the one on the left does. So that's pretty nice. And then additionally, the one on the right doesn't have certain circles for edge points where the circles are actually not really well measuring the spotting events. Like you can tell that like there's multiple spotting events that are being mapped as one spotting event, and we don't want that. So it's better to avoid that completely. So yeah, the bigger one is better. However, in generating these images, I can tell you it took a lot longer to render the one on the right than the one on the left.
Oh, so here's an overview of the whole spot detection pipeline from the original image to the grayscale used by principal component analysis, and then to take that into spatial data points, which we can then use to find the spots with our Gaussian mixture model, and which gives us this final result, which is, here it is big. Look at all those little circles on the circles.
All right, so the next thing we're going to talk about is vein alignment. And one cool thing about our project, since we were working with researchers with ongoing research, is that some of the requirements or tools that they needed shifted as we worked. And so this came up in one meeting. They had a problem where the Prusi lab is trying to find some kind of correlation between the location of spots and the veins of the petals. And to do this, they take the original petal, they take an image of it, and then they perform some kind of chemical filtering to it to allow them to get a really nice crisp image of all these petal veins here. And so what they do at that point is they try and manually go in and overlay the vein image over the petal image. And as you could imagine, if you've ever worked around with some kind of photo editing where you're trying to move an image around and rotate it to fit a certain size, that takes a lot of kind of tweaking. And while it may be feasible to do for one image, if you're trying to process a whole ton of data like this, that could become very time consuming. And we thought this could be a great application for some kind of software solution to align these images itself.
All right, so for our vein alignment pipeline, we start off by doing something similar to the PCA that we did in the previous pipeline with our k-means clustering. After that, we found the relevant shapes that we need of each image, i.e. like the general outline of the vein image and the general outline of the petal image. And then we were able to find how these images were positioned differently by way of using a function and estimating that function. And then by using that function, we were actually able to fit the shapes to each other. So it was very easy to overlay one on top of the other and get the vein alignment that we wanted.
Oh, okay, so the first step in this pipeline is k-means clustering, which we essentially use to simplify the initial image that we get. So these pictures are a demonstration of k-means clustering in just over regular scatter plot data, which is in 2 dimensions. Our data is in 3 dimensions because it's in color space. But we're just going to look at this because it's easier to have pictures of. So like the expectation maximization that Jack talked about, k-means clustering is an iterative algorithm. In k-means clustering, you decide ahead of time how many clusters there are, and you feed that into your Python program, or you calculate it yourself. The first step is that the k cluster centers are randomly initialized, like in this first picture. And then based on the cluster centers, all of your data points are assigned to the cluster with the closest center. And then, so that's picture 2. And then, based on the clusters that you now have, you find the new best center for each cluster, which is defined as the centroid, which has a specific meaning that we're not going to get into. And then you repeat those 2 steps until you get to convergence, which is just, you've got the best clustering. And in our case, that enables us to take our initial image with many color values and take it to an image with only 3 color values. And then when we convert it to black and white, it's very simple and easy to find the shape of. So here's what the images look like after the pre-processing going into the vein alignment pipeline.
All right, so after that, we will start talking about, trying to extract the shapes that we want and try to match them to each other so that way they're easy to overlay on top of each other. One of the biggest challenges with this is that one of the inconsistencies between images that we have is that the ratio of background to actual petal in an image can vary greatly between 2 images. And in typical image alignment techniques, we're like trying to align based off of the full image. However, we don't want that for this. We really only care about aligning the 2 shapes. The rest of the background image does not matter to us. So one thing that we need to focus on with that is that while our images right now are the same size, that does not mean the 2 petal shapes will be the same size. So we actually need to go back and resize the images so that way the petal shapes sizes match more than the actual image sizes. And then after that, we'll still have 2 very different objects. If you recall from the initial pictures, we have one petal that is a solid yellow or a solid gray with darker gray spots on it. And the other one is a straight up black and white image with just a bunch of vein patterns. And while it's very clear to see from the human eye that these 2 images are related, for a computer, they are very different. One is a solid shape, whereas the other is a collection of a bunch of lines. So a computer trying to analyze those 2 shapes for similarities is very difficult. And so we had to be able to regularize the format of both so that way they were easier to compare. And to do so, we decided that we wanted just to have kind of like an ink blot test kind of picture with a black background and then a white silhouette of each of the shapes. So that way they would look closer to the same. And the algorithm we use to do this is called the flood fill algorithm. Essentially, the flood fill algorithm starts at a certain point of interest. For us, that will be a point of color. And from there, it will look at a bunch of its neighbors and find how many of those neighbors are the same and how many of those neighbors are different. And essentially the flood fill algorithm at each iteration will change a certain amount of close neighbors that are different to the same until it hits a point where it's changing too many. This algorithm worked really well to get the shape of the actual petal image, but for the vein image where a lot of the neighbors were different colors, i.e. black rather than white, it was very hard to get super close shading results, as you'll see in the next slide. So on the left is the petal image, which silhouetted really perfectly. On the right is the vein image, where you can see some of the middle that we'd want to be shaded in did not get shaded in, and some of the boundaries, especially in that top left corner, started to become white, which we didn't want at all. And so essentially we had to approximate a certain good enough place where the two shapes looked similar enough to compare without overdoing it for that vein shape. And we found that most results that were good enough looked something like two shapes similar like this. So next, now that we have our two shapes, we want to be able to translate them so that way they look the same. And in theory, there are two major types of translations that can occur between objects and an image. Those two are Euclidean transformations and affine transformations. Euclidean transformations are the kind of transformations that you'd see on your traditional XY Euclidean plane. You have your rotations, your translations, and your resizing. And then affine transformations instead also offer a third dimension, which allows you to rotate the image in a different way than just the simple XY rotation. For general purposes, the affine transformation would have been better. However, for our images, which are all taken from top down, they're all on pretty much a two-dimensional plane already. So we could actually just use the Euclidean algorithm, which is a nice thing to be able to use because it runs much quicker. And the way that the Euclidean motion calculation works is that we have these two shapes and we assume that there's a function of some form like ax plus by plus c that will translate one shape into the other shape. And so the goal of this algorithm is then to estimate our parameters a, b, and c so it fits that the closest, and then we will get that function outputted back to us. And from there, we can apply that function to one of the two shapes, and then they will be aligned in the same way. So then we get to our overall pipeline where we start with our original images. We pre-process and do the k-means clustering on our petal image. We flood fill them, and then finally, we translate and overlay them as such in the final result. The final result in a bigger image looks like this. As you can see, the veins map very well on top of the actual petal, and this is sufficient for our purposes.
Okay, now we're just going to briefly move on to the methods and outcomes. I noticed we're a little tight on time. One interesting decision that we made pretty early on was to use third-party libraries for a lot of the algorithm implementations. The main reason we did this was to save time that we would have spent implementing these algorithms and be able to apply that into other things. And this turned out to work really well for us because there was some amount of trial and error with different algorithms. So we would try a certain algorithm and realize maybe it doesn't fit exactly what we're looking for in our pipeline and need to swap it out for something else. And you can imagine that if we had to put all that time into developing and testing that algorithm only to scrap it, that's a lot of wasted time that we probably should have been working on something else. The obvious downsides of using third-party libraries is that in the process, we picked up some technical debt, which essentially means that we knew kind of what the algorithms were doing, but we didn't know all the nitty-gritty details that we may have been able to optimize the rest of our pipeline for. And so when we're making changes on the pipeline or trying to fix a bug or something, we might have to go back and relearn a little bit more about the implementation of the library algorithm before actually making that fix. And the other thing, the other con is that we lost a little bit of ownership in being able to customize some of these algorithms to specifically match our needs, and we may have been able to make them a little bit more efficient because of that. I'll go quickly through what we learned. We learned a lot about developing solutions for an ongoing project or ongoing research where there are some like changing requirements, and we had to be very flexible to be able to kind of move in different directions at any given time. We obviously learned a lot about image processing and the math behind it. And then the most interesting thing for me was learning about cross-disciplinary communication, as we were collaborating with people in the biology department who knew a lot about biology, but maybe not as much about the computer side of things that we were focused on. So there was some work going into kind of translating what they wanted from what we were able to do and stuff like that. And then lastly, we'll just briefly talk about the next steps that we would have liked to do if we had more time. The first one would be to expand the vein alignment pipeline to actually look for the correlation with the spotting events. As we saw earlier, we can already output where those spotting events happen, but we don't really know where the actual veins are. And as this is something that they're doing manually, it would be a good thing to apply if we could. And then the second one is on some images, and obviously this is a more complicated petal than many. We have some instances where on these larger spots, we might be estimating a few more spotting events than should actually be there. And then we also had some difficulty picking up edge spots, as Jack mentioned earlier. And lastly, I'd like to thank Professor Stratton for kind of guiding us throughout the whole project, and kind of pointing us in the right direction if we were getting stuck, as well as Professor Cooley and Poozy, who were a lot of fun to work with. And I think we all learned a lot about biology and flowers from them. So thank you. Any questions?
Yeah, so we already have one question, which was going back to the description of the Gaussian mixture model and expectation maximization. There's a classical problem in clustering, which is if you know how many clusters there are, they're relatively easy to find. But how do you accommodate a situation like this where it might not be easy to determine how many clusters there are ahead of time?
We kind of generalized what we did in this presentation, but in reality, to solve this problem, we actually use like a Bayesian estimator as well, which allowed us to start with a high number of clusters, and then using some other probability tactics, we were able, the algorithm automatically removed certain Gaussians that were not seen as relevant enough. And so we just kind of overestimated the amount of Gaussians we needed and let the algorithm do the work to get down to less Gaussians that were more appropriate.
Yeah, and that threshold that Jack mentioned is something that we were able to set in there. So if we noticed that it was cutting out too many spotting events, perhaps we were missing some, then we could lower that threshold so that we were removing less potential spotting events.
And so was that Bayesian model that you talked about something that you came up with yourself, or is it something that was kind of built into the literature or work that people had already done?
Yeah, no, it's a common variant of the Gaussian mixture model, which is just called the Bayesian Gaussian mixture model.
We were lucky enough that it was also implemented in OpenCV, or in scikit-learn, excuse me, which is the library we were using for our Gaussian mixture models.
Yeah, great. So we have another question with the comment that, detecting spots along the edges is, just hard to do in general. Do you have any thoughts about, next steps about getting even more accurate results for some of those clusters or spotting events?
Yeah, Owen, if you could go to the point cloud with the circles on it. Yeah, so one thing that I have been considering doing, and I'm kind of just working on for fun right now, is so as I mentioned before with the trade-offs of accuracy with the distance between larger points and smaller points, is that a lot of smaller points will not get accurately represented, especially the ones on the edge, because of their proximity to larger ones. So one solution that we've been considering is to window our data points and make them smaller, so that way certain smaller blotches will not actually be in the same Gaussian mixture model as the larger ones. And doing so will allow it to be modeled much more on an individual level, and that will potentially help get more circles for them. Additionally, as Abby mentioned, we use PCA to threshold out certain values. Because they're thresholded in such a way, we could actually include the gray background without including the yellow petal parts. And by doing so, we can figure out where there are certain edge spotting events that are, rather than being a center spotting event, if they're touching those gray, those other like gray table values. And by doing that, we can fix our estimation to like look more in a different center.
Very good. Any other questions? If not, that is the conclusion of our Whitman Computer Science Digital Capstone Conference. I specifically want to thank all of our presenters for their work and making us proud with their accomplishments in their senior year of the Capstone project. So a round of applause virtually to all of them. I also want to thank all of the attendees who came to listen to their work and supporting our students through their academic projects overall. Thank you all very much. This is the first time that we've run anything like this. I kind of hope we don't have to do something like this again, but if this is something that people might find valuable in the future, feel free to contact me or Professor Davis as the returning members of the computer science faculty for next year about how you would like to continue to engage with our program and our students. If you have ideas for future capstone projects that you think you'd like to send our way, please feel free to let us know, and we'd be happy to talk with you. All right. So with that, thank you all again, and we will sign off for now. Have a wonderful rest of your semester for all of you affiliated with Whitman, and best of luck for your future professional and academic accomplishments.